So a review of section 5.1, 5.2, and work in 5.3 is what we're going to look at right now. So sections 5.1, 5.2, and 5.3 all together here. I mentioned a new kind of angle measure that's very important that we get used to. And that angle measure is called a radian. Oh, my screen is being very bizarro. All right, I think that's better. And so I just want to talk about radians again. When we are playing around with angles, we have a reference line, and that's going to be the positive x-axis that we work from. And then when we measure an angle, we measure counterclockwise from our reference line, the positive x-axis. Okay. So let's suppose I pick an angle over here-ish. Let's pick that one. I'm hoping that I just found a 30-degree angle, which in radians would be pi over 6 radians. Now, we can count by pi over 6 moving around the circle. We worked on that a little bit the last class. So this would be 1 pi over 6 here. 2 pi over 6s would be here. 3 pi over 6s would be here, which reduces down to pi over 2. And again, this would be 2 pi over 6s, which reduces down to pi over 3. All right, so this is an important skill in trigonometry. So we keep counting 1, 2, 3. Over here would be 4 pi over 6s, which reduces to 2 pi over 3. 1, 2, 3, 4, 5 pi over 6 would be here, which does not reduce. And then 6 pi over 6s would put us over here, which would be pi. And if we sweep ourselves all the way around and back to the beginning, so starting here and we sweep around and back to the beginning here, that angle would be 360 degrees or 2 pi radians. So this angle right here could be considered 0 radians, or it could be considered 2 pi radians. Now, reminder, 0 and 2 pi are two totally different numbers. However, when they're interpreted as an angle on a circle, they both put us in the same position, right? So on the unit circle, I would be referring to this point right here, the point 1, 0. What we're going to look at a little more today is angles that are related through reflections. So I could reflect the angle pi over 6 through the x-axis, or at least the point I get here. And if I reflect that through, the y-axis, that's going to put me over here. So I reflect across here. That's going to put me at the point here. And now I have another angle of 5 pi over 6. And last week we talked about the idea of a reference angle. So although the angle, the standard angle that gets me over to that point right there, from here to there, sweeping that radius over, is 5 pi over 6. There is a reference angle here of pi over 6. All right, and that is referred to as a reference angle. Reference angle is the angle nearest to the x-axis. So reference angle. Now, there's nothing special about reflecting across the y-axis. I could reflect across the x-axis, and so I could reflect this point down here, and I'm going to get another point over there. And again, imagine sweeping around 1, 2, 3, 4, 5, 6 pi over 6, 7, 8, 9, 10. That would put me at 11 pi over 6 right here. So the angle to get there is 11 pi over 6. What's the reference angle for 11 pi over 6? Well, since it's a reflection of the point that had an angle of pi over 6, the reference angle is also pi over 6. Now, just like this point here can be reflected through the x-axis, this point here can be reflected through the x-axis, so that's going to put me down here. And what would the angle there be? Again, counting by pi over 6, 1, 2, 3, 4, 5, 6. That would be 7 pi over 6 to this point right here. And 7 pi over 6 is similar to 11 pi over 6, which has some similar properties to pi over 6 and 5 pi over 6. So in a little bit, in the next video, we'll calculate the coordinates of the point here, 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 and here, noting which quadrant they're in. Quadrants are important. Quadrant 1, quadrant 2, quadrant 3, right? Just like we measure angles coming around counterclockwise, we name the quadrants coming around, and quadrant 4, counterclockwise. So it is going to be important to us to be familiar with this idea of reflection, that we have a point that has some similar properties to the point that we started at over here. So quadrant awareness is important. Thinking about angles in radians instead of degrees is important, but we still have all that degree knowledge in our head, and that's going to be useful too as we go around. All right, let's take a look at identifying the coordinates of that point right there. So I'm going to bring this to a new screen. And let's see, I'm going to attempt to draw my own circle here. Not bad. And I'm going to draw in the axes again, y and x, equally not bad. And then I had my pi over 6 angle right here. And I'm going to refer back to degrees for this angle also, just to get into your memory banks, things you're familiar with. So we could, again, we call this pi over 6 in radians. And I mentioned last time, if you see an angle measure and it doesn't say whether it's degrees or radians, assume it's radians. Otherwise, we need to state degrees. So this angle right here is either pi over 6 radians or it's 30 degrees there. Okay. Next thing I'm going to do with this is I'm going to draw a triangle out of it by just coming down from this point of intersection on the circle. I'm going to come down perpendicular to the axis there to form a triangle. Now think about triangles again. The interior angles of a triangle have to add up to 180. So I have 30 here, I have 90 there. So what is left there? This angle right here would have to be 60 degrees up there. Now the next thing I want to take into account is the reference, the reflective version of that point down here. And if I do that and connect some dots here, and here's what I'm going to find on this triangle. I have a 30-degree angle up here. I have another 30-degree angle down there. So altogether, the complete angle combined here is 60 degrees. Due to the reflective properties here of going perpendicular to the x-axis, this angle over here is also 60 degrees. So I'm just going to pull this triangle out here. I've just made a new triangle out of my original one. That looks like this, and not my best sketch, but we're going to go for it. Ooh, that is, I'm going to try that again. Let's see, that's more like it there, I think. Maybe. Not bad, we're going to go for it. All right, so what are my angles here? I had a 60-degree angle up here. I had a 60-degree angle over here. And I made a 60-degree angle by putting two 30s together there. So this is an equilateral triangle that I have going on there. What are some things I know about this equilateral triangle? Well, if the angles are all the same, then that means these side lengths are all the same here. And in my previous picture, I was playing with a unit circle. Unit means radius equals 1. So that means the length of this green line here is 1. So that means this is a 1, that is a 1, that is a 1 there also. Due to the symmetry inside the circle here, this length from here to here matches this length from here to here. So that means I have a line right through here that bisects this side. So if I just look at the top of that triangle right there, my original right triangle, what do I know about this right triangle at this point? Oh, here's what I know. Back here, this was originally a 30-degree angle. I built the right angle, which forced this to be 60. This was the radius, which had to be 1. And due to this reflective point over here, I know that this side is now 1/2. So I know the y value of that point right here. And again, my goal here was to identify what are the coordinates of that point. And I'm getting close. I have the y value. How would I find the x value? And if you're thinking Pythagorean theorem, you are correct. Anytime we have a right triangle, Pythagorean theorem can come into play when we have the lengths. And the Pythagorean theorem says that if you take the measurements of the legs, square them and add them up, so that means I take my question mark squared plus my 1/2, put it in parentheses, then square it. That has to be equal to the long side, the hypotenuse squared. So now we can find that other missing side here. So let's do our arithmetic and a little algebra. 1/2 squared is 1/4. 1 squared is 1. Question mark squared is question mark squared. Subtract the 1/4 over, and I'm running out of room here. We'll just head over this way. So now I know that question mark squared is equal to 1 minus 1/4 or 3/4. Keep going. And to get rid of a square, we take the square root. So that means question mark has to be the square root of 3/4. Now, technically, when we square root a square, we get plus or minus. On this particular triangle, since I am in quadrant 1, both the x value is positive and the y value is positive. So for this particular point, for this particular triangle, I want positive square root of 3/4. Now, I'm looking at the 4 inside the square root and thinking, wait, I know the square root of 4. So I can take this a step farther. So plus or minus, this is the square root of 3 over the square root of 4. Square root of 4 is 2. So that means plus or minus the square root of 3 over 2. The 2 is not in the square root now. So the coordinates of this point right here would then be, since I'm in the first quadrant, it has to be a positive x value. Square root of 3 over 2 is x, and y is 1/2. So I've now found that. So we have a special angle, 30 degrees, or pi over 6 radians. And based on that special angle, I now have this point here, square root of 3 over 2, 1/2. So I'm just going to take that information, combine it with this reflection inside the circle, and then label all of the points coming around for the special angle pi over 6. So again, oops, line tool, that was messy. So that's going to be about here-ish. And what we've just identified is that the angle of reference here, which is also the standard angle, is pi over 6 radians. And the point of reference there for this is going to be the square root of 3 over 2 for x and 1/2 for y. And I'm going to resist turning this into a decimal on here, but I am going to calculate the decimal and see if it looks right on the screen. And I can see the way I drew my point, I think 1/2 looks pretty good as the y value. I'll buy that, right? 1/2 would be right about there. Let's see what square root of 3 over 2 is on a calculator just to see if it looks right. So you can either bring up a calculator or in Google just type square root parentheses 3, close parentheses, divide by 2, and Google says, hey, you want a calculator? So 0.866, 0.866. And does that look reasonable on my picture? 0.9 would be about over here. Yeah, I'm a little bit over, but it's close. That's in the ballpark. I'll take it. So this is approximately 0.87 to 2 decimal places, which would be about 0.9 to 1 decimal place. And on my picture, that looks all right versus 0.5. But since 30 degrees is a special angle in the world, and pi over 6 is its counterpart in radian measure, we want to be familiar with this number square root of 3 over 2 versus 1/2 for the other one. Now reflecting coming around, we have these other angles. So we have the reflection of that point through the y-axis over here. And that gives me a reference angle over here, right? Remember, reference versus standard angle. The reference angle would be pi over 6. The standard angle coming around here would be 1, 2, 3, 4, 5 pi over 6. Remember, pi is 6 pi over 6. So this angle is also 5 pi over 6 when I measure it from the standard reference line. Now I'm now in quadrant 2 instead of quadrant 1, and in quadrant 2, x values are negative and y values are positive. And so this point right here, due to the symmetry of a circle, must be the point negative square root of 3 over 2, comma 1/2. So when I was solving this equation back here, and I got either the positive or negative square root of 3 over 2, the positive square root of 3 over 2 is related to this triangle, and the negative square root of 3 over 2, it turns out, was related to that one over there. Let's keep going around here. So if I reflect this point through the x-axis, then I'm going to end up over here. The reference angle for that point, remember, reference angle is to the closest part of the x-axis, that would be pi over 6. The standard measure for that angle would be sweeping around this way like that. So pi is 6 pi over 6, so this angle right here must be 7 pi over 6 to get to that point. And now I am in quadrant 3, and in quadrant 3, x is negative and y is negative. So that point right there must be the point negative square root of 3 over 2, comma negative 1/2. To get this last point here, I could either reflect this point through the y-axis or the green point through the x-axis, and they're both going to lead me to the same position, right about there. And that point, again, like all of the other points here, has a reference angle of pi over 6. And that's just the positive, that was a little messy, that's just the positive angle to the closest part of the x-axis. Direction is irrelevant. Just want to get to the closest x-axis I can. So pi over 6 there. To sweep around to get to that point, we could count by pi over 6 again. So we had 1, 2, 3, 4, 5, 6 pi over 6s to get here. 7, 8, 9, 10. That would be 11 pi over 6 to get to there. So that's the angle in standard position. Reference angle is pi over 6. And again, due to the symmetry of the circle, I just have to think about signs here. X is positive in this quadrant, in quadrant 4, but y is negative. And so this point right here must be square root of 3 over 2, negative 1/2 for the point. There's many other special angles. I'll list those very shortly.